Hello, MAT134 students. So because of the winter storm, today lecture 104 is cancelled and I need to record a makeup lecture for this lecture, we were supposed to cover section 7.3. But because this week was very dense and I think I didn't have enough time to go into all details of section 7.2, so I decided to record two sections, both 7.2 and 7.3. So let's start with 7.2, section 7.2. First, let me give you a summary of the lesson in this section. This section is about computing in trigonometric integrals. Integrals like exponent of sine, another exponent of cosine, dx. Integral like this or like this, which has tangent and secant in it. So our goal in this section is to compute such integrals. So the idea is, a strategy is that if I mentioned the strategy as a rule that you can memorize it. Then I will explain why we have this for those who are interested. So the rule is that if you have odd number of sine, cosine, or tangent, if there are odd number of sine, cosine, or tangent, or even number of secant, then we use a substitution, then use the substitution. U equals the other one. But what do I mean by other one? For example, if you have odd number of sine, the other term in this integral is cosine. So you should do u equals cosine, the substitution. Or if you have, for example, odd number of tangents, then you have odd number of tangent, the other term is secant. So you do substitution u equals secant. Or if you have even number of secant, the other term is tangent. So you do substitution u equals tangent. So then use the substitution u equals the other term. How do you do this substitution? By isolating or separating du, separate du, and convert everything else, the rest, into u. How do you do this conversion? Using two identities. Using identities sine squared plus cos squared equals 1 and 1 plus tangent squared equals secant squared. Using these identities. So this one should be used for this integral and this one should be used for this integral, obviously. Okay, if you are fine with memorizing things, just memorize this general strategy and you are good to go. But for those who are interested, why such we have such thing. Where did this odd and even came from? The idea is this. I will explain the reasoning behind this strategy for those who prefer to understand and don't memorize this rule. So what is the idea? The idea is that using these identities, I can convert even number of 2 or any other even like 4, 6, even number of sine and cosine to each other. And I can also convert even number of tangent and secant to each other. So if I want to see that a substitution, for example, u equals sine or u equals tangent, such thing works. Let me list all of them. We have 4 kind of substitution: u equals sine x, u equals cos x, u equals tangent x, and u equals secant x. If I want to see if this substitution works, the idea is that I should be able to separate du and convert everything else into u. That's the idea. So what is du in each of these cases? This one, du is cos x dx. For this one, du is negative sine x dx. And for this one, it is secant squared x dx. And finally, for this one, it's secant x tangent x dx. So so the idea is that I want, if this substitution is going to work, I need to separate this and convert everything else into u. What is u in the first case? It's sine. So I need to separate one cosine and convert the rest into sine. The rest, to be convertible to sine, need to be even number of cosine. But separated one cosine as well. So in total, I need to have odd number of cosine. Basically, the same parity as I see here. So this odd number of cosine comes from this, because in the substitution u equals sine, the derivative of sine is cosine, and it has odd number of cosine in it. So that's why we have odd number of cosine. Similarly, if you want to do substitution u equals cosine, the derivative of cosine is negative sine. This has odd number of sine in it. So I need odd number of sine to be able to use u equals cosine as substitution. Also for tangent, derivative of tangent, it's secant squared. It has even number of secant in it. So if you want to use this substitution and this substitution wants to work, you need to have even number of secant. So that's why if you have even number of secant, then you need to do substitution u equals tangent. Finally, for the last one, if u equals secant, once you want to use it, then you need to separate this and convert everything else into u. U is secant. So basically, this term is u itself. That's not a problem. The problem is converting the other terms into u. So I'm only interested in how many tangent I have. So there are odd number of tangent in the derivative of secant. So that means I need to have odd number of tangent to be able to use substitution u equals secant. Because if I have odd number of tangent, I can separate one of them as this, and the rest of them, which is even number of tangent, I can convert to u, which is secant, using this formula. That's the idea. So whatever you prefer, you can just memorize this strategy and use it without understanding the reasoning behind it, or you can understand where this strategy came from and just check it every time that you want to use it. If you want to use, for example, this substitution, check derivative of tangent. it has even number of secant, and check if you have even number of secant here or not, then you know if it works or not. Whatever you prefer between these two things. Okay, now that we have discussed this, uh, let's discuss one special case that you can't use this strategy. What happens if, for example, in this integral, if this is odd or this is odd, odd number of sine or cosine, you are good. You can use this strategy, these substitutions, and go for it. But if not, if both of them are even, before talking about that, what happens if both of them are odd? Then both of the substitution is good. So this and this are both satisfied. So basically you can use any of these two substitutions, but choose the one that is simpler. The same for this integral. If both these substitutions are good, then you can basically do any of them, but do the one that computation is simpler. So that's up to you to choose the simpler one. Now let's talk the other case that you can't use any of these substitutions. So in this integral, you have this and these are both even numbers. So none of these substitutions u equals sine or cosine work. So what should you do in that case? Let me explain that in a separate page. When you have this integral where both m and n are even numbers. So you have even number of sine and cosine. So though this strategy doesn't work, you can't do this substitution, you can't do this substitution. What you should do is using these identities. Then use the identities I have even number of sine, also even number of cosine. So I want identities about sine squared and cos squared. Sine squared is 1 minus cos 2x over 2, and cos squared is 1 plus cos 2x over 2. So you need to use these identities. You need to use them repeatedly. For example, if the exponent, one of the exponent is 12, 12 is even number. So every time you use this, it's like you have, you make the exponent roughly half. So it becomes 12 divided 2, it becomes 6. 6 divided 2 becomes 3. At some moment, you get odd exponent. So the idea is to repeatedly use these identities and make the exponents smaller and smaller by making them half-half until you are in these situations that you have odd number of sine or cosine. Then you use this strategy. So the idea is to use the identities this repeatedly until you have odd number of sine or cosine. Then use the substitution in the strategy. Substitution in the previous strategy. Okay, that's the idea. You may want to ask what happens for this integral if none of these happens, if you don't have odd number of tangent and you don't have even number of secant. There is a general solution in that case as well. It is mentioned in the textbook, but it's more complicated than these cases that I discussed, and we rarely use it in this course. So I will skip talking about it in this lecture. Now let's move on to the questions, to the both multiple choice questions and activity questions at the end, and apply this strategy that we already have seen. So the first integral is this. Assume that even this suggestion is not there. You look at this. This is the type of the integral sine to some exponent, cos to some exponent, yeah? So either the substitution u equals sine or cosine should be used. Let's see how many sine and cosine I have. How many sine and cosine I have in this? I have no sine. No, having no sine means sine to the exponent 0. So how many sine I have? I have 0 sine x. How many cosine I have? I have 3 cosine x. Is this odd? No. 0 is an even number. So this is bad. But this one, I have 3 cosine. It's odd. This is good. It's odd. So I can use a substitution. Do you remember a strategy? Let's just quickly look at it. When you have a good number of sine, cosine, tangent, or secant, then you use the substitution which equals the other term. That's important. The other term. So going back to this example, this is a good number of cosine. So I should do u equals the other terms, sine. U equals sine x is a good substitution. What is du? Du is cos x dx. Now, how do I do this substitution? By isolating du first, separating du, and converting the rest into u. So first isolating du, which is cos x dx. That's du, cos x dx. I isolate. What is the rest? The rest, I already wrote dx. I already wrote one of these cosines. The rest is 2 more cosines. So we have cos squared. This one, it's just du. I need to convert this into u. U is sine. So how should I convert cos into sine? Using these identities. So in this case, this identity, sine squared equal plus cos squared equals 1. So using that identity, this is 1 minus sine squared. And sine is u. So this is 1 minus u squared. And after replacing these in terms of u, I have 1 minus u squared du. So the correct answer is option A. Feel free, if you like, that pause the video and try each question first yourself. But because this is a recorded lecture, I won't wait for you to do that. Okay, what about this one? Look how many tangent and this is the type of tangent secant integral. So I need to count how many tangent and secant I have. I have no tangent. That means I have 0 tangent. How many secant I have? I have 6 secant. What did I want? I wanted, if you remember, odd number of tangent and even number of secant. Odd number of tangent. No, this is even number of tangent, so that's bad. What about secant? I needed even number of secant. That's even number of secant. 6 is even. So this is good. So I need to do substitution. U equals secant, number of secant is good. So I should do substitution, the other term, which is tangent. So I should do substitution u equals tangent. Then what is du? Du is secant squared dx. And after doing this substitution in this, I need to do isolate or separate du, which is secant squared dx, and convert the rest to u. What is the rest? I already wrote dx and two of these secants. The rest is 4 secants, secant 4x. Now I need to convert this secant 4 into, let me actually write it on the bottom of the page so I can a lot of space to do the computation. So this is secant squared squared. And secant squared, do you recall which equation I need to use? 1 plus tangent squared is secant squared. That's the identity that I should use for the conversion. I need to convert into tangent. I need to convert all these secants into tangent. And that's the identity that I should use. So secant squared is 1 plus tangent squared. Let me write it down. This is 1 plus tangent squared squared. And the tangent is u. So that's also 1 plus u squared squared. This part is just du. So the whole substitution becomes 1 plus u squared squared du. That is what we get here. Exactly. So but the option, the answer is what substitution I need to do. The answer is just u equals tangent. I could just do the correct choice at this moment, but I want to go over all the details behind every single question. So that's why I do even more than what you are asked to do in these questions. The last multiple choice question in this section is this. We want to compute this integral, and the hint is given using this identity. This is one of the identities that I mentioned at the beginning in the summary of the course. So if I want to use that, I see that I have 1 minus cos. Here is I also have 1 minus cos. So I notice that this should be the same as this. So this 2 theta should be 6x. So what should be theta? This should be twice of theta, twice of something. 6x is twice of 3x. So I notice that for theta equals 3x, I get that 1 minus cos 6x, which is 2 theta, over 2 is sine squared theta, which is 3x. But here I have 1 minus cos. So let me move this 2 to the other side to have just 1 minus cos on the left. So we get this. So that means that I can substitute this with this. So 0 pi over 6 integral root 2 sine squared 3x. So if I apply a square root, I get root 2 and root sine squared. But root sine squared is absolute value sine. By the way, this is a typo. It's pi over 6. That's absolute value sine. Root of something squared is absolute value that thing. And by a simple argument that for x between 0 and pi over 6, that's argument that I want to do. X is between 0 and pi over 6. Then the angle free x is between pi over 2 and 0. And between 0 and pi over 2 in the first quadrant, here, you see that sine is positive. This is sine axis, this is cos axis. In the first quadrant, sine is positive. So I don't need absolute value. Basically, I get that absolute value is redundant in this case. If these numbers were something else that you will land in this quadrant, or this quadrant, then sine would be negative. Then absolute value would be a negative sign. You need to do a sign argument. But in this case, absolute value is redundant because I'm in the first quadrant. I get sine 3x dx. And the correct answer is B. That was all multiple choice question. Now let's do activities. Actually, there are a lot of them in this section. Let me don't do them in order. First, let's do this last one, which is not relevant to what I talked about at the beginning of the session. For these kind of integrals, you just have some formulas in the textbook that if you have a question like this in the test or final exam, the formula will be in the formula sheet. So you just need to use the formula. That's it. So that's why I haven't talked about it at the beginning. It's nothing. It's just put the formula in front of you and just write down the answer. So let me show you the formula. This is the formulas that I'm talking about. Formulas 15, 16, 17 in the textbook. In this case, it's one of them. We had cos, so it's number 17 that we should use. We should use the formula number 17. If we use that in this question, what we get is, let me, I don't know the formula uh, by heart, so I need to look at it. Let me bring up my formula on another device. Yeah, that's this. The formula, it says that we have sine m minus n, sine 7 minus 4 x over twice of the same number, 7 minus 4. That's just, let me show you the formula again. It's just formula number 17. It's the first term in the formula number 17. Now the second term is minus sine of the sum of these 7 plus 4 x over twice of 7 plus 4. And plus, this is an indefinite integral, so of course it involves a generic constant. So if you simplify this, 7 minus 4 is 3. So you get sine 3x over 2 times 3, 6, plus sine 7 plus 4 is 11 over 11 times 2 is 22 plus c. That's the final answer. Very simple. You just have the formula and you use it. Then let's talk about the second easiest question in this list of the problem is number 2. So if I want to compute the area under this graph, so I need to integrate my function. That's my function. That's the equation of the graph. Integrate sine 3x dx from here up to here, from these 2 points. But I don't have, I have this. This is 0. So from 0 up to something that I need to find. So let me find this point. What is the characteristic of that point? It's the x-intercept of this graph. So let me compute it here. So it's when this graph is 0, x-intercept. That means sine is x is 0. And let's look at when sine x is 0. Let me first draw unit circle. And mark all the points that sine is 0. That's sine axis. 0 is this point and this point. All the points on the circle, out of all the points on the circle, only these 2 points have sine equals 0. So you know that there are infinitely many answers. There is like 2 pi that you can add to answers, and then you again come back there. So there is infinitely many of them, but I'm interested about these two. One of them is the first one, 0 here. And then I'm interested only about the next positive answer. The next positive answer will be rotating pi. So this is pi. There are more answers. For example, 2 pi is another answer. It's a point here. 3 pi or even negative pi. Negative 2 pi. These are all answers of this equation. But there are before 0 or after this point. The 2 points that I'm interested is 0 and the next positive answer. So it's 0 and pi. So basically I got that I should compute the integral from 0 to pi sine cubed dx. Let me do this computation on the next page. Let me cut this. And paste it here. Okay, so this is the form of the integral that we discussed at the beginning. It's integral of an exponent of sine and exponent of cosine. So let me count how many sine and cosine I have. I have 3 sine and 0. I don't have any cosine. That means I have 0 cosine. If you recall the strategy, or if you look at derivative of sine and cosine to see parity of them, so basically what I'm interested is odd number of sine and cosine. This is not odd, this is even, so that's bad, but this is good number of sine that I have. So this gives a substitution. What is the substitution? The substitution is u equals the other one, not sine, the other one. Sine and cosine are paired in the integral, tangent and secant are paired. So the other than sine, it's cosine. It's cos x. Then du is negative sine x dx. Good. So let me substitute u equals cos x in this integral. Things that I need to do. First, separate or isolate this term, du. So let me write it separately. That's du for me. Then I should write the rest here. What is the rest? First of all, I didn't have any negative sign, but I added a negative sign here. So it's a negative sign to cancel each other. dx, it's there. Out of signs, one of them is written here. So we have 2 more sign to write it here. Okay. So this part is du. Now I need to write this part in terms of u. What is u? U is cosine. So I need to convert this into cosine. And the key identity is sine squared plus cos squared equals 1. So sine squared is 1 minus cos squared. And that is 1 minus u is cosine. U squared. So this integral is basically minus 1 minus cos after substituting in u 1 minus u squared du. Okay, good. So this integral was definite integral. It was from 0 to pi. It was the values of x from 0 to pi. Uh, but in this definite integral, now the variable of integration is u. So I should mention from what u to what u. U is cos x. When x is 0, u is cos 0. And when x is pi, u is cos pi. What are cos 0 and cos pi? My best friend for trigonometry. If you don't use it, it's the worst thing that you can do to yourself when you are working with the trigonometry. The best, the more easiest and the most optimal answer to most of trigonometry question is about it's hidden in very simple unit circle. So cos 0 and pi. Where is 0? It's here. Let me use another color. 0 is here and pi is here. What is cos 0? That's the cos axis, horizontal axis. So it's 1. Its unit circle means the radius is 1. And what is cos pi? It's this much, which is negative 1. So this is negative 1 and this is 1. So what do I have is integral from 1 to negative 1 minus 1 minus u squared du. I usually prefer to have a smaller number on the bottom rather than a larger number. And I have an extra negative sign on the back. So these two suggest me to swap these two. When you swap two things, you get a negative sign, which cancel this extra negative sign. So basically this becomes from minus 1 to 1 with positive sign on the back of 1 minus u squared du. And this is very simple integral to compute. What is antiderivative of 1 minus u squared? It's u minus u free over free. And I evaluate at negative 1 and 1. When you plug 1, you get this. When you plug negative 1, you get this. So this is 2 over 3 minus minus 2 over 3, which is 2 over 3 plus 2 over 3 or 4 over 3. That's the answer for this. Now, let us do these two. First, the first one. Let me memorize it. Secant 3 tangents. And I do it on a separate page. Integral secant 3 tangent. Okay, this is the type of secant tangent example, and I need to count how many secant and tangent I have. How many? I have 3 secant, 1 tangent. What was good for me, if you remember? If either you forgot, that's why I explained at the beginning. Where those odd even numbers came from? From the derivative of things. So let's assume that you are at the middle of exam and you forgot. Was it odd good, even good? I'm confused. I don't know what to do. You can just construct a strategy whenever you want. Look at the derivative of tangent and secant. If you have u equals tangent, the derivative or du is secant squared dx. And when you have secant, du is secant tangent dx. So in the derivative of tangent, I have even number of secant. So even number of secant is good for me. Do I have even number of secant? No, I have odd number of secant. So that's bad. And I can't use this substitution. That means that this is cancelled. How about this? If you want to use this, U itself is good. I can easily replace any secant in terms of U substitution. But the problem is converting the other term, tangent, to secant. So I'm only interested in this term. This is odd number of tangent. So in my integral also, if I have odd number of tangent is good for me. How many tangent I have? One tangent. That's good. One is odd. So I can use this substitution. So that's the idea. You can just memorize the strategy and use it, but it's very simple reasoning behind it. And if you understand the reasoning, then you are confident that even if in the exam you confused and you forgot the strategy, you are not worried. Just look at the derivative. So this is good number of tangents. That means I should do substitution u equals the other term, not the tangent. The other term, secant. Du is secant tangent dx. And if you isolate this term, secant, I think that's a lot of a space, secant tangent dx. That package is my du. So what is the rest that I should write here? Dx is used, tangent is used, one of the secant is used, so two more secant. Now I need to convert this into u. Look at u. What is u? U is secant. I have no problem. This is just u squared. I don't need even the identity. And this is du. So this integral is integral u squared du. And it's very easy to compute because antiderivative of it is u free over free plus c. And don't forget to replace back u in terms of secant, in terms of x, which is secant x, plus, or if you like, that's the same as secant cubed x. Okay, good. That's the final answer. Now look at the last problem, which is this. Integral of tangent cubed. This is secant tangent type. So let me count how many tangent and secant I have. Even if you don't see secant, the type of the problem is either sine cosine or tangent secant. It's paired to each other, even if you don't see it. So I have no secant. That means I have zero secant. Let me use some color like red. Zero secant. I have free tangent. What was the good number of secant and tangent? Tangent odd was good, so this is good. And secant even was good. Zero is also even, so this is also good. So I have two options. Both substitution work. Actually, one of them is simpler. Uh, and it's better to do some simpler one, but just out of like for training, for like practice, let's do both of them. I solve this question in two different ways. Once using the substitution that is because of this, the other one using substitution that is because of this. You will see that one of them is simpler. So it's up to you in test or exam to or assignments to choose simpler one. If you did harder one, that's fine, but it should be not so hard that you should be able to finish the computation. Okay, let's do one of them now. So let's do, for example, let's look at du first. For this one, I should do u substitution, the other one. So when secant number of secant is good, the substitution should be u equals tangent, and du is secant squared dx. And when number of tangent is good, I need to do substitution. U equals secant, the other term. And du is secant tangent dx. Okay, let's do one of them in this page, next one on the next page. Both are applicable. So let's do, oops, this one here and this one here. So let's for now focus on this substitution. What do I have? I have du is this. So I need to isolate or separate this. So I need to write secant tangent dx. That's my du. I isolated. Let's look at the terms. Dx is used. One of tangents is used. So two more tangents remain. But I used a secant here that I didn't have originally. That means I need a secant in the denominator here. This is the same as that because these cancel each other. So this is the du term, and this is the rest that need to be converted into u. Converting into u in the denominator is simple. That's just u. But in the numerator, let me open up some space. But in the numerator, this one, tangent squared, I need to write it in terms of secant. So what should I use? The identity that we have used it before as well. 1 plus tangent squared equals secant squared. So tangent squared, the identity is 1 plus tangent squared equals secant squared. So that means tangent squared is moving 1 to the other side. It's secant squared minus 1. And that means secant is u. This is u squared minus 1. So in summary, after doing all the substitutions, we get u squared minus 1 on top, u on the bottom, and du after. Okay, now I should compute this integral. That should be very easy one for you if you like learned the material before test one very well. So it's just when you see this, it should be very obvious that if I do this and separate terms as this minus this, then each term is a power term, and I'm basically done. So if you do that, u squared over u, which is just u, let me write it in the next step, minus 1 over u du. So that's u minus 1 over u. And antiderivative of u is u squared over 2. Antiderivative of 1 over u is ln absolute value u, don't forget absolute value, plus a constant. Is this my final answer? No, there was no u in this. It should be in terms of x, so I need to substitute back u equals secant. So I get secant squared x over 2 minus ln absolute value secant x plus c. That is one possible answer, which is completely correct. And this is the easier solution. So out of these two options, the computation for this is simpler. So when you have two options available to you, choose the one that is simpler. Now, let's do the more complicated one, but I will finish the computation just to show you that both options are possible. And for one question, you may have different solutions that are all correct. So now let's do the other substitution that still works. U equals tangent. Then du is this. So I need to separate. Let me do it in another color, like green. So I will separate du, which is secant squared dx, secant squared dx. That's my du separated. What else I have? I have this free tangents untouched. Dx is good, but sine secant squared I have here. I didn't have it before. So I need to put it in the denominator to cancel it. This part is du. And I need to convert these into u. U is tangent, so the top is easy to do. The top is just u cubed. The bottom, I need to convert it to tangent. So I need to use the identity that is conversion between secant tangent. It's 1 plus tangent squared equals secant squared. So secant squared is 1 plus tangent squared, which is 1 plus u squared. So in summary, we get u free over 1 plus u squared du. So that's the thing that you may want. You may had this question before that I mentioned. Go for the one that is easier. You may want. You may ask that. How do I know which one is easier? Of course, you don't know beforehand. But after doing the substitution, here I got that. Here I got this. By just looking at these two integrals side by side, let me bring that to the other page. Which one looks simpler? Definitely this is simpler because I can consider it as this, and each term, this is basically subtraction of two power terms. That's it. Very simple. But this one, you can't do it like that. You need to be more smart and do some more trickier stuff to solve this. So out of this, definitely this is easier and you go for it. But let's solve this as well. I need to do some trickier stuff that you may wondering why. The idea is that we will learn more about this in next week when we talk about integration technique partial fractions. We will discuss actually how do you integrate a general polynomial over polynomial. At this moment, we haven't discussed that, so I try to explain things without using that lecture. The idea is that I have u free, u cubed on top, but in the denominator I have u2. So if I want to make a multiple of this on top, then what should I do? 1 plus u squared. To get u cubed out of it, I need to increase the degree by 1 or multiply by u. When you multiply by u, you don't just get u cubed, you get u plus u cubed. So I create this term on top as a multiple of denominator. Let's do that. U cubed plus u, that's u plus u cubed. That's what I want to construct. But I can't do that. This is not the same as that. It should be the same. So I need also to subtract u. This is the same as that, but written such that I have a term which is multiple of the denominator. over 1 plus u squared, or if you like, u squared plus 1. I would prefer 1 plus u squared. So now it should be clear. I created this package to be as a multiple of denominator. Why? Because I wanted to use the same trick as the previous question, that I separated terms such that I get simpler things. I need to separate this and separate these terms as two separate integrals. So I would do a package is u cubed plus u over u 1 plus u squared. Another package is minus u over 1 plus u squared. So it's like two separate integrals that we need to compute. This one, it's very simple because this is just u times denominator. This is u times 1 plus u squared. So the ratio of them is just u. So the first integral is just u du. That's why the idea behind all this, why I started like that. Minus, for this one, what should I do for that one? For that one, if you learn the previous material well, it shouldn't be hard to see that. Oh, I need a substitution for this. Why? What was the two criterion to use substitution? One of them was to see a layers of terms and go one level inside. The other one was if you see a term and derivative of it also appears on top. So I see 1 plus u squared and derivative of it, which is 2u, forget about the coefficients. So it's just u appears on top. So that's an obvious sign that substitution in 1 plus u squared is good. So let me do that. Let me do 1 plus u squared as a substitution. Because I already used the substitution u, I cannot call this again u. I need to use call a new name for this substitution. Let's call it, for example, W. So I want to do substitution W equals 1 plus u squared. Then dW is 2u du. So this package u du is half of dW. Good. Now this integral after the substitution becomes 1 over w, 1 over 2 dw. Am I good? Yeah. Now it's easy to compute these integrals. The first term, antiderivative of it, is just u2 over 2, u squared over 2, minus antiderivative of this is ln absolute value w. So it's half of ln absolute value w plus a constant. Now, this is not a good final answer because my final answer should be in terms of x. These are in terms of u and w. I need to substitute back. First, substitute back w as 1 plus u squared. Then what do you get? You get the first term. I haven't done anything with it yet. And the second term becomes half of ln absolute value 1 plus u squared. W is 1 plus u squared. Plus c. But 1 plus u squared is always positive. It's never negative. So this absolute value is actually redundant. Okay, good. And finally, the final step to use this is in terms of u, to replace back u in terms of x, which is u equals tangent x. If you do that, you get tangent squared x over 2 minus half of ln absolute value 1 plus U is tangent, so it's 1 plus tangent squared x plus c. If you like, you can replace 1 plus tangent squared as secant squared and make things simpler. And actually, it's a nice exercise if you like to check why these two are both correct answers. That means if this is a correct answer, this is also a correct answer. That means that both this term and this term are antiderivative of what we are looking for. So that means these two should be the same up to a constant. That means they are different by a constant. That's a good exercise if you like trigonometric exercise. Try to convert these using trig identities into this. They are not equal, but you get one of them is the other one plus a constant. That's, if you like, you can do it as exercise, but it's not necessary for this course. Okay, that's the end of this lecture 7.2. So I record a separate one for 7.3. Thank you.